So hi, today I'm going to present the paper Algorithmic Classification on Expansion on Negative Rational Base. So we start off with a motivated example, 8 over 5 in the base and negative 3 over 2. So unlike base 10, we see there are two main differences. The first one is the representation is non-unique, and also second, the recurring length is different. So this motivates us to answer two questions. The first, does there exist representation for any rational number m over n in the negative rational base? And if there is, what's the procedure to find all representation m over n? So now we'll begin with the definition of the number system, where we assume NB is bigger than DB and NB/DB is coprime. And the digit sets D, and the digits within the number system, we will set it as 0 to NB minus 1. And out of the four expansions, the most important is the primary recurrent expansions, which we will denote as PRE. And the other three will be just analog to base 10. So we'll list the main theorems here, the complete residual system theorem, and also theorem 2.34 and 35, which gives the existence and the upper bound of representations of m over n. So we'll first consider the first two expansions, which we will define the integer expansions recurrence relation, in which we will input a number n0 in the set 1 over db. After uniquely deciding the digits di, in which we have the resultants ni must be in the set 1 over db, we will find a unique integer expansion. That's generalizing the example. We can get the theorem here, which every number n0 has a unique integer expansion. So now we'll move on to why the complete residual system CRS theorem works, which we'll be discussing primary recurrent expansions, PRE, which recurs right after the decimal point. And we'll give a proof on the system using the reverse algorithm. So the most important property is the bound, in which it limits the number of numerators of PRE for a fixed Q, and the other property will be used later. We will also define the notation, cursive P, to be the set of numerators of PRE for a fixed Q. And after defining cursive P, we will prove our goal, which is to prove the numerators form complete residual system, mod Q. So we'll get some motivation. Consider the base negative 3 over 2. So if we list all PRE with period 1, there are only 3 of them, which is not enough to fill in the complete residual system, mod 5. But when we list all the PREs with period 2, we find the numerator does form a complete residual system, mod 5. So in general, when the length of the PRE is long enough, that we know eventually the numerator does fill in the complete residual system. So now we'll define the reverse algorithm, in which is used to determine whether a fraction has primary recurrent expansion or not. So it's a division algorithm, in essence, in which the AI and NI are uniquely decided. But we realize the value of AI actually represents the digit choice. In particular, if we consider the left example, when Ni equals to Nj, we know that Ni over Q has a primary recurrent expansion, where the digit choice are AI. And we see that N0 over Q does not have a primary recurrent expansion, because N1 equals to N6. And on the example on the right, we see that N0 equals to Nj. We see that again, N0 over Q has primary recurrent expansions where the digits are AI, and we see that N over Q has primary recurrent expansion. Now we'll use this spiral-like graph, or we'll use this graph to illustrate the relevant lemmas. So we see that the numerators, N0 up to Ni minus 1 in the tails, are denoted as the numerators that does not have a primary recurrent expansion. And for those residues inside the circle, Ni up to Nj minus 1 are numerators that does have a primary recurrent expansion. So now we'll move on to the goal of proving the numerators form complete residual system, mod Q. So we'll first pick an element N0 in the set Q, apply the reverse algorithm. Then we will construct the set C1, containing the residues of the red numerators here, Ni up to Nj minus 1 mod Q, which are the numerators of primary recurrent expansion. Now we'll pick an element H0 in this set, and we'll construct the set C2 similar to how we construct the set C1 before. And eventually, we can express set Q as a disjoint union of non-empty C1 up to Ck's, which proves the complete residue system theorem, because every residues in those sets correspond to a primary recurrent expansion. Now we will show the connection between the complete residue system theorem and the existence of representation. So we will give some motivation from base 10. Consider we want to show the existence of representation of 17/14. First, we multiply the base so that the denominator of the new fractions is 7, which is co-prime to 10. And then we will split into two fractions where the red one has an integer expansion and the blue one has a primary recurrent expansion. Now we can add those two expansions together and divide the base to get the expansions of the original number. But to generalize it to a general base, suppose you want to show the existence of 577/2686 in this base. So we'll first decompose the denominator into three parts, where the first part only contains factor of dB, the second part only contains factor of NB, and the rest is Q, which is co-prime to NBdB. So we'll first determine the length of the non-recurring part after a decimal point, which we call y, by this expression, in which we'll multiply our number by base to the power of y, so that we get rid of the factor of NB in the denominator of our new fraction, similar to how we multiplied 10 in the previous example. Now we'll split it into two fractions where the red a⁴/7 has an integer expansion and the blue fraction has denominator 1343, which is co-prime to NBdB, so we can apply our complete residue system theorem to find C⁴/1343, which has a primary recurrent expansions, and we can just add those expansions and divide the base to get the expansion of the original number. So we see that the complete residue system theorem actually guarantees the existence of representation. But now we'll try to find all representation of M/n. So unlike base 10, the recurrent expansion in the general base is non-unique. So first, the initial steps of finding all representations are basically the same, but to find all representations, we need to find a condition in which we'll limit the number of C that we'll test. So we'll be having the first condition is by the Bezier lemma, and the second condition is a necessary condition, in which after limiting the number of C that we'll be testing, we'll input those C's in the reverse algorithm to find which exactly C has a primary recurrent expansion. And for those who have, we'll just put it into this equation, the decomposition equation, to find back the integer expansion. So let's give an actual sample. So we found that there are only 3 C's satisfying both bound B and the congruent C1. So which are these 3? And we'll input these 3 in the reverse algorithm, in which we find only 2 of them has primary recurrent expansion, while the left one does not have a primary recurrent expansion because there does not exist J such that N0 equals to Nj. In particular, we have N1 equals to N7. And then we can just substitute back the 2 primary recurrent expansions that have into the decomposition equation to find back the expansion of the original number. So now we have just shown the existence of representation of any M/n, but for the upper bound, theorem 2.35 asserts that there are at most floor plus 1 recurrent expansions. The idea is that consider the lower bound and the upper bound of the primary recurrent expansion, in which we see inside the bound there are at most floor plus 1 integers that are apart by dBq. So we see that if all of these C have primary recurrent expansions, then M/n achieves that many recurring expansions. So we'll summarize the results of the paper by the following diagram, in which this answers the question, the first and the second question in the beginning. But for a further extension, we conjecture that there may be infinitely many non-recurring and non-terminating expansions of M/n if we disregard our reverse algorithm and freely choose our digits from 0 to n, so from 0 to nb-1 without any restriction. But this could be left as a further research topic. Thank you.